you very much all for coming. I hope you'll find it interesting, and thank you, Dave, for organizing this. So I'm actually happy to see many condensed matter people here because the title is meant to be homage to Phil Anderson's book. More is different, but it's going to be different in different directions. So yeah. So in theoretical physics and mathematics, counterexample plays important role in pointing out the gap in the prevailing framework. So one of the pivotal moments in the 19th century mathematics was when Karl Weierstrass discovered the function that is continuous everywhere, but is not differentiable almost everywhere. So his construction was contrived, and it wasn't clear whether it has anything to do with natural phenomena. But nevertheless, the Weierstrass function showed that there was an error in the intuition prevailing among mathematicians at the time, that a continuous function should be differentiable, except for a finite number of points. So, so this led to reshaping of the framework of calculus in the 19th century, and that's why you have to learn things like epsilon and delta in the first year undergraduate. So you can ask whether that was a good thing after all, but it was nevertheless significant. So today I'd like to point out a gap in another prevailing framework, which is the Wilsonian paradigm in the effective theory. So we all know that the basic thing about physical world is it's a hierarchical. And Ken Wilson actually formulated it in a mathematically rigorous way in the language of effective theory. So his idea was that for each energy scale, there is a set of laws called effective theory that describes physical phenomena at that scale. And we can be ignorant of more fundamental laws at a higher scale. And he formulated this in the language using renormalization groups, for example. And this was great. For example, the idea of renormalization that was invented in the mid-1940s looked very artificial, hiding infinity arbitrarily in some natural constant. But from the point of view of Ken Wilson, it came out very naturally. He was a German student, went to Cornell for many years, I understand. And so, for example, the pion theory is an effective theory of QCD. And we don't need to know about QCD to discuss pion physics. We can be ignorant about the physics far above the QCD scale. As far as you are interested in physics below QCD scale, then you are okay with pion theory. Okay, so the basic assumption that goes into this kind of idea is that as long as the effective theory satisfies consistency conditions that are evident at the applicable scale, then it can be derived from a more fundamental and mathematically consistent theory at high energy. And that's why we can be ignorant about high energy. We write down low energy effective theory, and then we can expect that it comes from more fundamental theory. So in this talk, I would like to show you that this assumption is false with graph. So of course, I mean, even in gravitational theory, we can use effective field theory approach, and this has been used, and it's very useful. So we can actually form, in many circumstances, we can treat Einstein's gravity, cosmological constant, Einstein Hilbert sum, and finite number of matter field as effective theory. And for example, Hawking radiation calculation was done using this. People believed it. That's why string theorists worked on it for more than half century to try to make sense of it. The fluctuation of a cosmic microwave background caused by quantum effect during the inflation calculated. That's why people like Jamie Box, Sunil, and Kimi Wu tried to working hard to detect polarization because they believe this calculation, right? And this is my favorite example, the correction to Newton potential. So this is the Newtonian potential. There is a correction, important correction by classical relativity. And so it's suppressed by speed of light. And so it disappears when the speed of light is infinite. But then there are quantum effects. And so there is an H bar. And there is a explicit, a very concrete number 41 over 10 pi squared. You can calculate this. And this number is for Einstein gravity. And if you include other matter fields, the different number. For example, if you the next important one would be neutrino, and so if you have neutrino, there's the function which depends on the mass of neutrino. But you can calculate, and we trust this is the correct prediction. Of course, it's very hard to measure it in the experiment because this combination G Newton H bar divided by C speed of light cube is a Planck length square, and Planck length is 10 to the minus 35 meter. So I don't expect we can measure this immediately in the future, but this is the correct number, nevertheless. Yes.
So usually when you have something like this that's calculable, it's because it's non-analytic in the, so it's.
It's a coefficient of log.
Pardon?
It's a coefficient of log. So that's why the coefficient is scheme independent.
Say that again.
So if you calculate the one loop correction
Right.
to the gravitational force, this is a correction to the log piece, the
Oh,
coefficient.
okay.
Yeah, so that's why
That's the non-analytic.
it's non-analytic in that. Yeah. Thank you. Yeah, so that's an important point. I should have mentioned that. So because it's coefficient of log that we can actually scheme it. So there's a famous paragraph in Joe-Polkinski's lecture note in 99, the effective field theory and the Fermi surface. Presumably, no field theory we have ever encountered, and perhaps no field theory of any type is complete up to arbitrary high energy. They're all effective theory, valid up to subcut. And that's a very healthy attitude. So we don't aspire to have complete theory. That it's supposed to be, we are all working in effective theory, and that. So then he explains the application of that, the Fermi surface, and they explain BCS. It's a beautiful lecture that if you're interested in effective theory, they're highly recommended. But gravity is different. And there are people who believe that this assumption may not work, that any quantum theory gravity must be complete by itself. So you might have heard an argument for this type. So this is something I do when I give public lecture, but so I kind of hesitate to do that to this audience, but let me do that just to give one example of argument. So in gravity, the separation of UV and IR degrees of freedom fades, and the separation of the degrees of freedom is essential for the idea of effective theory. So for example, suppose we build a Planck scale accelerator and collide a particle, right? So how much short distance we can see? Well, so without gravity, we say that the resolution is inversely proportional to energy because that's the sort of wavelength of quantum particle. But if you include gravity, there is a Schwarzschild horizon, and we cannot observe things inside of the Schwarzschild horizon. So therefore, the resolution of space in terms of accelerator of energy AE should be the maximum of these two numbers. And that is square root of 2 G Newton H bar divided by C3. And this combination is a Planck length. So this means that even theoretically, even in principle, even in this kind of Gedanken experiment, you cannot drop distance shorter than this. And in physics, we take the attitude that if there is even no in principle way of observing this, they don't exist. And so it's different, that you cannot postpone your decision of completing the theory forever, that you should stop at the Planck scale. So this type of idea, that this calls into the question of validity of Wilsonian paradigm when the gravity is included, because the gravitational theory may not be considered as an effective theory. This type of idea, and also non-string construction at the time, it's already like 20 years ago, motivated the Qumran-Buffer to conjecture that there are conditions that any gravitational field theory must satisfy, but which are not obvious from low energy consideration alone. So if we can produce such condition, then that would be a counterexample. That would satisfy the basic assumption that as long as the effective theory satisfies consistency conditions that are evident at the applicable scale, it can be derived from a more fundamental and mathematically consistent theory. And so producing such example would falsify that basic assumption. So what I'd like to do is that to produce for you some such condition. Now, so this is a work in collaboration. So I would like to point out a couple of work that I did. One is with Daniel Harrow, he's now at MIT. And this is already like 6 years ago. This is with Yifan Wang at NYU. I was on sabbatical thanks to Fiona at the NYU last fall of 2023, and then so I worked with Yifan, and so I just published it last summer. So I'd like to mention these two things. These are just like Weierstrass function. These are not directly, that's not seemingly applicable directly to natural phenomena because it works when the cosmological constant is negative. But this is the sort of, I view that as a proof of concept that at least in this circumstance, there are conditions for low energy theory that are not obvious. And so if it exists in this circumstance, it can exist in other cases and possibly more realistic cases. And during the talk also, I would like to point out that if you assume that this kind of condition can be extended to more realistic situations, then it can be relevant to some observation and experiment that we can do now. Okay, so I'd like to discuss that too. Okay, so this is the situation. This is a sort of proof of concept. So I'm going to discuss this in the idealized setup, where you can use this idea of Juan Maldacena called ADS-CFT correspondence. So we consider the gravitational theory with negative cosmological constant that the space is asymptotically becoming like a hyperbolic ball at T, and then you add time, and you produce uncertain space. So the idea of Juan Maldacena is that any quantum gravity theory in d+1 dimensions over here in uncertain space is equivalent to scale invariant quantum field theory, conformal field theory, defined on the boundary of space, which is the d-dimensional series. So this is the idea. So this is great because you can conformal field theory is better defined. We know much more about this theory without gravity. So we can use this as sort of first principle in understanding gravitational theory. So using CFT as a definition of quantum gravity in ADS, I'm going to derive several non-Wilsonian constraints on gravitational theory that are not obvious from the low energy point of view alone. Any questions so far? This is what I would like. So this is not our real world, but this is a proof of concept that there are such non-Wilsonian conditions that for gravitational theory. Okay, so in fact, there are two main threads of non-Wilsonian statements that we have been exploring for the last 30 years or so. So there is one idea called that the fundamental theory should not have any adjustable parameters. Pretty old idea before my birth. And so we quantify that in the form of distance conjecture, I will explain later. And there is another idea called there is no global symmetry in quantum gravity, which is pretty old idea before my birth. And this was quantified in the language of weak gravity conjecture. So there are two threads of non-Wilsonian constraints. And these are recently proposed for asymptotic flat space, so should be applicable to our real world. This has not been derived from fundamental principle. Some of these are derived from fundamental principle in ADS, which I'm going to talk.
What are phi and q?
I'll explain. I just showed this, but I wrote that as quantified, so I just showed that there are equations that comes with that. Okay, that's clear. So I would like to first tell you about the first thread. And no adjustable parameter. So 1949, so that was the year when autobiographical note of Albert Einstein was published. This is actually very interesting reading. And so there's a chapter in the book where he explains the notion of natural unit, where you take G Newton to be 1, speed of light to be 1, Planck constant to be 1. And he goes on to say that then, namely in this natural unit, the only dimensionless constants could occur in the basic equation of physics. Concerning such, I would like to state a theorem, which at present cannot be based upon anything more than upon a base in the simplicity, namely the intelligibility of nature, that there are no adjustable constants of this kind, that all the constants should be explainable from fundamental principle. That's the idea that Einstein proposed. It's more like a hope. So Kuhn-Buffer and I proposed what's called distance conjecture. So it's actually a series of statements of what that we expect for low energy gravitational theory should satisfy. And the conjecture zero is sort of modern formulation of what Einstein said, that every parameter in quantum gravity is an expectation value of a dynamical field. Namely, for each adjustable parameter, there must be some dynamical field. And then that parameter is the expectation value of the field, and therefore can be varied by changing the expectation value. So this is the zeroth order conjecture. There will be few more that I will mention later and prove, but this is the first one. Okay. It's actually easy to prove in the space. And in fact, I outlined the proof in my summary talk at the Strings 2022. And so I have been actually writing a paper with younger colleagues, making this more rigorous, and it's now 60 pages. But so I haven't published it yet, but I'll give you an outline of how this works. And so the idea is the following. So this you have this ADA-CFT correspondence. So suppose there is actually continuous family of gravitational theory with adjustable parameter lambda. Okay, so suppose there is some kind of family of gravitational theory parameterized by some continuous parameter lambda. By ADA-CFT, there must be the corresponding conformal field theory whose Lagrangian is also parameterized by lambda. The continuous parameter, so you can deform it continuously. And so you can ask, well, what happens if you change the value? Well, the Lagrangian changes so slightly, and so there is some kind of new term in the deformed Lagrangian. This is a perturbation theory that you learn in undergraduate quantum mechanics class. But both of them are conformal field theory, so therefore the term that appear here satisfies a particular property. It's called, technical term is called exactly marginal. So exactly marginal perturbations appear when you deform this parameter in conformal field theory. Now you go back to Maldasena's paper, and they ask, well, what does the existence of exactly marginal operator means for gravitational theory? And it means that there is actually a dynamical field in gravitational theory. That if you have exactly marginal operator in the conformal field theory, in the corresponding gravitational theory, there must be a massless scalar. This follows from Maldasena's dictionary, such that the expectation value tells you the variation. So this is basically the proof of the idea. Fleshing it out requires 60 pages, and but I have it's almost done, so I believe this is correct. And so the parameter is an expectation value of some scalar field in UDS. So this proves the zeroth order conjecture, the conjecture number 0 that I propose with Cohn. But this statement itself does not provide very useful constraint. This is the constraint, this is the true statement, but it's not very useful since you say that, well, low energy theory has parameters, so this does not make sense. But it may not be, because what appear to be adjustable parameter in low energy may be fixed by some potential in high energy or more fundamental theory. So for example, the standard model of particle physics has 19 parameters. So here, David Polisa is not here, so I can safely say there are 7 more parameters if you include the massive neutrinos. If you are at the meeting during the weekend, you know what I'm talking about. And the lambda CDM model, the cosmology has 6 parameters. But we don't say that they don't make sense, right? So they do not contain, there are no dynamical fields corresponding to these parameters. Most likely, they are still expectation value of some field, but all these fields are fixed by some unknown potential in high energy. So this by itself is not very, this is a true statement. Conjecture 0, the letter of conjecture 0 is true, and they proved it in ADS, but nevertheless, it's not useful. So what Conrad and I did in that paper was to quantify this statement. So we looked through all known string theory construction at the time, and try to come up with more constraints. And there are 2 constraints I would like to point out. One is that suppose you have this parameter family of the theory, then we pointed out in all known string constructions, there is always direction which goes to infinite distance. And if you go to infinite distance, low energy effective theory gets broken down within a finite distance. because there is always a tower of right particle coming out. And these two statements are true in all known string theory construction. After we published the paper, this is already like 18 years ago, and many string theorists studied this example, try to find a counterexample. No counterexample have been formed in this case. So we are happy with this paper, but it was sort of one of those sad papers. And so for the following, well, this is a mathematical version of this, so I'm just flashing it up. So if you're a high energy theorist or experimenter, you know Slack spires, Inspire. It's still called spires. Now it's called Inspire, and it has a X post. It used to be Twitter. But, so once in a while, when they have something, they have citation in database. So once in a while, when they have interesting citation phenomena, they post on X. So this was one of my paper with Cameron. So this was published in 2006. There was X post about this. My paper was Cameron, and it's kind of embarrassing because it's kind of one of those very sad paper. We were very happy with the paper, but the citation is like 10 at best. And there was some year where it's actually, I checked this, there was 0 citation in that year. So it was kind of one of the sad paper. But then it shoot up about 10 years ago. And then the Inspire said that this paper is a sleeping beauty. So the question is, who woke up? Who woke up 10 years ago? Okay? So anybody a suggestion? Well, the BICEP 2 announced that there is actually they detected B-mode polarization, and there was a suggestion that it can be out of primordial origin. So I was actually a deputy chair at the time. So far was the chair, and I had noticed that where Jessica Garrett is right. Actually, about a month before this announcement was made, Tom walked into my office and said the BICEP is going to make an announcement. And I said, do you know about tensor scalar ratio? He said 0.2. And I told him, and I think he remembers it, but he teased me afterward that great, it's going to kill string theory. And so there is a reason for this, and it is this diagram. So this horizontal axis is the tensor scalar ratio. The vertical axis is the range of inflation. Okay, and so I wrote over here. I didn't explain it, but suppose there is a scalar field whose expectation value determines some dynamical parameter of the theory, and if it travels distance bigger than or comparable to Planck scale, there is a particle of order e to the minus alpha phi coming down. So in this diagram, actually, this alpha was very generously, conservatively estimated. But so let me explain the diagram. So there is thing called the Rice bound that anybody who knows cosmology knows the Rice bound, which is that in order for inflation to happen, the inflaton should go in some distance in order to have 60-40. And so this is a lower bound. So any consistent theory should be above the inflation should be above that. But distance conjecture says that no, inflaton cannot roll too far because otherwise low energy effective theory breaks down. So in this diagram, I will tell you the alpha was rather generously estimated. In our paper, we said alpha is above the Planck scale, but this is like 1/10 of Planck scale, so it's rather generous. And then, but then it crosses over here. So that means that even for this generous statement, that if R is more than 0.2, then the theory is inconsistent. That's what it is. And so that's why, so I was like, well, our conjecture was actually wrong. But so anyway, so this was what happens. And it would have contradicted our distance conjecture. So the good thing about this outcome is that it actually alerted string theorists who are doing all these formal mathematical things to note that, that this can actually potentially be very interesting. And in fact, so as I said, this is a rather generous estimate of alpha. And if you can strengthen this estimate, it can go down. So then it can become competitive for the future experiment too. So for this reason, it's very important to determine the value of this alpha. In my paper with Cameron, we just said that it should be above the Planck scale. But we didn't quantitatively say what is the upper bound for alpha. So I have been working in various ways to try to sort of determine if there is a way to determine the lower bound of alpha. And so I'm happy that actually, at least in a rather simple setup of ADS, that I was able to come up with a lower bound for alpha. So we showed that
Hiroshi, can I ask a question? What's the cosmology? So are these like string monodromy inflation models? Are they like an
yeah, so I think that this is generous enough so that string monodromy is below here.
Okay, so it's
So it's okay.
It's inside.
I have long discussion actually more than 15 years with Eva about this, whether string monodromy is in contradiction with distance conjecture. But here it's okay because I think it's generous enough, so it includes string.
But the general feeling is that it is consistent, like those models are consistent.
Well, I can give another seminar about the question. I have about string monodromy construction. So this is a very string monodromy is very because I think this is the only so far I know the only credible way from top down from string theory where the inflaton can go much above the Planck scale, and so therefore can be potentially top down construction of inflation. But I have some question about construction and also relation to distance conjecture. But in any case, for this diagram. So I still stand by with my statement I made to Tom that if it is 0.9, it's going to kill string theory. And that's I think the value.
That's another question. So there's also these models that solve the hierarchy problem by letting the Higgs mass slowly flow. They also have long traversal. Are those are those also ruled out by distance?
Well, I haven't. Yeah, I'm not familiar with this. I need to know about this. Yeah, so
Okay.
this is the relax song.
Yeah.
Yeah.
Okay.
I should look into that. So anyway, so with EFAM last year, so we this idealized setup of ADS, we actually be able to fix the lower bound. And it's actually much stringent than what we expect. So this is like 10 times the Planck scale. But actually we found that it's actually really like square root of 2 over 3. So this actually in this case this is actually rather stringent. So this is not directly applicable to this case because this is ADS. But we can do something like that in Planck space. Then or in the expanding universe, then it's very interesting. So I like to understand this. But this is the first step. Okay, so let me go to the other thread. Okay, so I'm doing very well with my time. So this talk is meant to be half an hour. So that if you I'm happy to take any questions. But let me go to the second stage. So no global symmetry. And so this was actually conjectured by John Wheeler. And it's written in his joint paper with Wisner called Classical Physics as Geometry Analysis of Physics. It's an interesting reading. And so the modern formulation of what he said, or they said in the paper, is that there is no global symmetry in quantum gravity. So we proved this statement again in ADS, and this is with Daniel Harlow. So this proof makes use of the relation between holography of quantum gravity and quantum error correcting code in quantum information theory. So in quantum error correcting code, so the error correcting code is basically the idea that you have to introduce redundancy in order to protect your data. So in classical computer, you make just many copies and you check. But in quantum mechanics, you have this non-Xerox principle that you don't have, there is no unitary evolution to make multiple copies of the same thing. So you do more interesting things. You consider high dimensional space, you consider some non-trivial subspace, and you encode the information. And the way you do it is that you have various physical qubits that feed into logical qubit. But this is exactly how ADS-CFT works. So in ADS-CFT, there are some local excitation in gravitational theory, which are encoded in the entanglement of quantum field conformal field theory state at various spatial locations distributed. So this is the idea. And so this actually, so there's a very nice paper by Joyce here called Happy Code, named after these four authors. This is an example of quantum error correcting code to exhibit exactly this type of property, the characteristic property of ADS-CFT correspondence. And so you can therefore utilize idea from quantum information theory. And actually, Daniel and I didn't know about this theorem when we were writing paper. We learned this after the fact, but it's essentially the quantum information idea. There is a thing called Easting-Kneel theorem. And that forbids the following thing. So suppose with the question of whether you can implement some kind of global symmetry in the error correcting code. So namely that there is some kind of continuous group action on each of the physical qubit. And then there comes the corresponding action. And can you act this transversely? Namely that whether you can act this in a way that do not couple with a different qubit, so that whole thing is invariant. So this theorem says that you can do that. Okay, so because of this correspondence between the quantum error correcting code and the holography of quantum gravity, we can implement that. And I noticed that, so this shows that the symmetry does not exist if it acts transversely. But it's actually exactly what Noether's theorem does. Noether's theorem says that in conformal field theory, symmetry acts transversely at the point, because Noether charge is an integral of Noether current. So more seriously, what it means is that if you have a symmetry and if there is a symmetry generator, and if you separate the conformal field space in the boundary, this joint point, then the symmetry generator is a product. This just follows from the fact that the Noether charge is an integral of Noether current. But there's actually also a more mathematical version of this, which works in discrete symmetry also. So because of this, and then using this idea of instant Knurr theorem, we are able to prove that there is no global symmetry. Okay. So this was a very happy circumstance where the idea of quantum information theory was very useful in understanding quantum gravity and actually help us prove some theory about quantum gravity. So there is actually a very interesting paragraph in the introduction of the book about theoretic games by von Neumann and Oscar Morgenstern. And this is about interdisciplinary work between different areas of physics. The physicists work on individual programs, some of great practical significance and others less, mine is less. Unification of fields which were formally divided and far apart may alternate with this type of work. However, such fortunate occurrences are rare and happen only after each field has been thoroughly explored. So quantum information theory has been explored for decades by many people, John Alexei et al. And string theory has been developed since the time of John Schwartz. And so these are thoroughly independently explored, but there are once in a while there is a happy circumstance where there are interactions between them. But I should point out that this happy code work is already 12 years. So it's about the time we should have many more happy circumstances. And certainly this bridge will help us. So in each of these buildings, Ginsberg Center and Downtown, we're going to thoroughly explore each of the respective fields. But now that we have bridged, so we have more circumstances to meet with each other, so that we are very happy thing. So thanks to Fiona and the other people.
So, I have a question on that before you move on. So is it an analogy that you're able to carry over, or is it literally the proof?
These are mathematically equivalent states. These are proof. So namely that it's a totally different physical phenomena, quantum information and quantum gravity, but mathematical structures are equivalent.
Okay.
So therefore, we can use one mathematical theorem applicable to the quantum information theory to prove theorem mathematically to quantum. Our paper was published in mathematical journal, Communication in Mathematical Physics. Yes.
So does this apply to symmetries with or without anomaly?
Oh yeah, so this is a very interesting question. So we have actually a chapter about symmetry. So you are talking about two anomaly. Yeah. So in that case, you can still construct it. So then you have to go into the realm of non-invertible symmetries and so general symmetry. I mentioned something about general symmetry later, but there are a lot of interesting generalization of this concept. For example, there is also generalization of this higher form symmetry. But
the conclusion still holds.
Yes.
Would it hold for the axion, the Jacobin?
Sorry?
Would it hold for Petrov?
I'll come to that. Yes. So so this is a spontaneously broken symmetry.
That's true.
Yeah. So this actually there. So our paper is like 160 pages, and so there's actually also a chapter about spontaneous symmetry breaking, and it works in spontaneous symmetry breaking too. But it requires more discussion. Okay, but I think just like in the Einstein's expectation that there are no adjustable parameters, that this statement that there are no global symmetry itself does not give you a useful constraint because we don't know how it is broken. So for example, standard model of particle physics has B minus L, baryon minus lepton global symmetry. But it should, according to the idea that there are no global symmetry, it should be violated or gauged in high energy. But we don't know how it is done. We'd like to know and quantify it because, for example, I'd like to tell to my colleague at Dune or Hyper-Kamiokan, there's a how big their water Cherenkov detector should be in order to detect the proton decay, for example. And so we want to be useful. The situation is very similar, analogous to the absence of parameter. So in the absence of parameter, what seems like adjustable parameter may be fixed in high energy. So we want to have a more stronger constraint. So this was actually proposed as weak gravity conjecture by Nima Al-Kani-Hamed and collaborators. And the statement is that in any low energy theory described by Einstein gravity, Maxwell field, and finite number of matter field, if it has an ultraviolet completion as a consistent quantum theory, there must be a particle with charge Q and mass M, such that this is equal to 1. So this all is happens, then the gravitational attraction between such pair of particles is smaller than the Coulomb repulsion between them. And so that's why it's called weak gravity conjecture. This is true, of course, in standard model. The electric force is much stronger than gravitational force as we experience in everyday life. But this conjecture that it says it should be true for any quantum theory gravity. So for example, Cliff has a very interesting paper trying to prove this statement. And so this has not been, so even in ADS, this has not been proven. There is an ADS version of this, which actually is true for ADS3, but not the higher ADS. And so I'd like to understand that. And it's potentially interesting. Just like distance conjecture may have implication in TMB polarization measurement, this may have implication on the mass of a neutrino. So in fact, I have this is one of my most speculative papers. I usually don't like to write speculative paper, but this is one of my speculative paper where we actually stretch the envelope a little bit, and then you apply the weak gravity conjecture, and actually somehow derive the inequality between the dark energy density and the mass of a neutrino. So there is this mysterious relation that the fact that the density of dark energy, excuse me, the density of dark energy in the universe is about the same order as expected the value of neutrino mass to the force, and unclear why that should be. And but if you believe my speculative argument, then there is actually an inequality between. And it also depends on whether neutrinos are Majorana or Dirac. And this is interesting because, so for example, underground experiment typically measure the difference of neutrinos, but this depends also on the absolute value of neutrinos. But there are also cosmological observation which determines of absolute value of cosmological constant. So this can be tested, and in fact, it's sort of consistent with the current observation, but it's actually rather it's rather tight. So I know that, for example, next generation of Shinbei experiment like Shinbei S4 or Lightbird can also determine the sum of mass of neutrinos, and because it can affect the structure formations and things like that. And so that can actually rule out or confirm our inequality. So that I think is very interesting.
Rosie, can I ask a question about the proof with Dan with Harlow? So you were saying you didn't know yet how to quantify how much breaking would allow you to kind of sidestep the statement. You quoted this Easton-Pinel theorem. Does that theorem provide any?
Yeah, so this is something so they have actually some idea of how to sort of modify it.
We have a paper about approximate global symmetry.
Yeah, so this is the kind of direction I'd like to understand.
So there's some notion of a margin that you can.
Yeah. So you have some paper where, so this is yet another interesting potential interaction between quantum information and quantum gravity. So he has this idea of how to actually generalize this when symmetry is slightly broken.
I see.
And so if there is if you can translate with a bridge,
right.
if you can translate
Need that bridge?
You can, because it's like the axion being alive or dead depends on this, right? Maybe we'll talk about it. Like, if these quantum gravity effects are large.
Yeah. So
For the
it's
action.
very important to quantify.
Yeah.
Yeah. Okay, so, So-
Rosie, could you show your allowed space plot again? I'm just trying to read the numbers.
yeah, so actually I forgot, I tried to remember where I took this slide from. I think this might be one of the cosmology things.
Because I think
This is Dirac, this is my run.
my recollection is Desi's supposed to produce an interesting constraint on.
Oh, yeah. So this is not updated with this.
I don't think it's produced an interesting constraint yet, but it's supposed to get there before CMBS4.
Do I recall correctly that there's some interesting statements about the Higgs mass, these conjectures?
Oh, so that's different. So that's about that's another speculative paper I wrote with Cameron. And this is about potential for scalar. So this is more in the direction. So this is about you're talking about this
Yeah.
paper by Hitoshi and the collaborators, I guess. And so I wrote with Cameron about the property of potential for scalar. And there was a conjecture, they called the zeta conjecture. And so there was we wrote this conjecture about the property of the scalar potential. And after we put the paper, we realized that, well, actually, what we said wasn't exactly right. So there was we need to refine the condition to make it consistent with all known examples. So we are writing this, and then Hitoshi actually wrote a paper that our original proposal was inconsistent with the property of Higgs, and so that was how it happened. So, but this is not that one. This is different. So this is a hazard of writing too many speculative papers. So this is what I expect. There are two threads of constraint and low energy effective theory that are not Wilsonian. So in the face value, these are not these are counterexamples. So if we take it seriously, and some of that has been proven, that this is non-Wilsonian statement. And there are one more thing I want to say. So for the elastics, I already briefly mentioned in answering Xia's question that the notion of global symmetry has been greatly generalized. This is actually a very nice paper that Anton Kapustin and a collaborator wrote about 11 years ago. And so there's this generalization of P-form symmetry, but nature charge is co-dimension P+1. So therefore, charged objects are p-dimensional extended objects. And so these are very important for and many applications. Also, non-invertible symmetry. These are related to anomaly also. And so in that case, so we run in undergraduate a symmetry makes group, and that's why the mathematical method in physics course we teach group theory. But now we should probably teach algebra because the generalized symmetry. The symmetry charges do not necessarily make a group, but in the more generally algebra with a non-invertible element. So traditional symmetries are zero form and invertible. And so in that language, absence of adjustable parameter in quantum gravity can be regarded as absence of -1 form symmetry. So this is very interesting because that means that the first thread of conjecture, the conjecture Wilsonian. Not some of that are conjecture, some of that are proven. First thread of non-Wilsonian statement and second thread of non-Wilsonian statement are actually unified in the context of general symmetry. So it'd be interesting to understand whether this more quantified version of distance conjecture I and Cameron formulated and weak gravity conjecture Nima, Al-Khani Hamed and collaborator formulated, are they also quantified? And this might help to actually strengthen both of these statements. So this is something that I think is interesting to explore. So the summary is gravity is different. And but in more detail, there are constraints of low energy effective theory of gravitational systems that cannot be captured by the standard Wilsonian paradigm. And so I mentioned two threads. And in ADS, we can quantify and prove part of these conjectures. But I'm working to strengthen these results and also generalize them to space-time with zero or positive vacuum energy, where we can actually use it to understand the world. But so far, this is proof in concept. It shows that just like Weierstrass function was, by the way, Weierstrass function turned out to be very useful in the 20th century, that it was used for model of Brownian motion and fractal geometry. So you never know, but at least for now, I'm presenting this as a sort of proof of concept that such conditions. That's all. Thanks.